Hello, 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 everybody. Root Beer here with the very last question on the 10th grade level 2003 Cayley competition. Okay, so if you are just joining me for the last question, you can click the link in the description and get this contest, try it for yourself. Or more likely, you've been following along, you've been watching with me as I go through them, as I attempt my solutions, and maybe you're itching for a new contest. You can click the other link. It'll take you to the CEMC website, and you can try any other of their past contests. Cayley, too easy for you? Try a format. You want more of a written question? The Galois started this year, and that is a 10th grade level written style competition. Okay? But as I say, we're going through question number 25. We're going to wrap up the Cayley in this video. So I've got my pen ready. Hopefully you've got yours. Let's take a look at question number 25. Angle BAC is said to be laceable if distinct points x1, x2, x3, all the way up to x2n. So I guess they're specifically talking about an even number. It can be found so that x2k minus 1, so 2k is even, 2k minus 1 will have to be odd. So odd points are on AC, just as we have in this picture here that has yet to actually be explained. X2k is on AB for each value of k, so I guess even points are always on AB. And we have here AX1 is equal to X1, X2 is equal to X2, X3. So all these lengths are equal all the way up to X2n back to A. So it all comes back to A. And all these lengths, as we sort of follow this sequence around from A to X1 to X2 to X3 to X4 to X5, all these lengths are equal. So immediately I'm thinking there might be some isosceles triangles in here. Okay. So, for example, the angle 20 degrees is laceable as shown. When it's 20 degrees, we go x1, x2, x3, x4, x5, x6, x7, and x8, and then we're all the way back to A here. Okay, so we do have an even number of points, and they say that it's laceable, so all these lengths in here should be the same length. The number of laceable acute angles. So we want acute angles, so it's got to be less than 90 degrees. That's fine. Whose sizes in degrees are integers. So nothing like 22.5 or anything like that. And that's something we need to keep in mind. So we're looking specifically for integers, and they have to be acute angles, so nothing bigger than 90 degrees. And we just need to find out that number. Doesn't look like there's going to be that many. 3, 4, 5, 6, or 7 are our possibilities. Okay. So, I'm noticing, as I've mentioned, that we've got a lot of the same lengths here. AX1 is the same as X1, X2, is the same as X2, X3, X3 to X4. These are all the same length. So I'm wondering if it's possible that it might work down to eventually you hit some sort of equilateral triangle, and that's what bounces it all back. Okay, so if we did an equilateral triangle, actually, can we get an equilateral triangle? I'm not entirely sure, but, actually, now that I think about it, I think 60 degrees will be laceable because it'll just be an equilateral triangle. So actually, let's go to our notepad and see if that'll work out. So B is on top. We go A, B. Oh, we want black, not the dark blue. And we go over. So B is on top. And let's say that this were 60 degrees. Here's our A. Here's our C. If I go out a particular distance and find me an x1. And if I go up by that same length, we're going to have an equilateral triangle. Because it's isosceles, we can see that right away, so these are both going to have to be 60, and then when I solve for the remaining angle, that has to be 60 as well. So this brand new point x2 is going to have the same length to A. So 60 degrees is laceable. I don't know how helpful this will be, but at least we have 2 examples of laceable angles. That's not bad. I can't think of anything else off the top of my head. I wonder if it will all come down to equilateral triangles, and this is just the case where an equilateral triangle pops up immediately. Let's see if we can go through the construction of sort of the lacing of 20 degrees, and maybe that'll give us a little more insight. We'll see where all these equilateral, I keep saying equilateral, I want to say isosceles, because I know there are isosceles triangles. I don't know there's necessarily an equilateral one. But where all these isosceles triangles might be and how they might work together to maybe create an equilateral triangle, or maybe there's a particular angle we'll need to bounce back and keep all the even stuff on one side. I don't know. But for 20 degrees, we start off, and I'm actually not even going to say 20 degrees, I'm going to say red dot. Okay? When I do it this way, if ever I need to make a computation, of course I can plug the 20 degrees in, but I'm trying to keep it as general as possible. So that angle there is just red dot. And maybe as I'm working through these isosceles triangles, I'll find other angles that I can compute in terms of red dot, or they'll help come together in a particular way, and I'll have maybe 5 of them around a point or something like that, and that'll force red dot to be something. Maybe it'll be forced to be a multiple of 3 or something like that. I don't know, or a power of 2 or something. 20 doesn't fit either of those, but not the point. Maybe if I just keep it generally, sort of vaguely in there as red dot, I might then be able to find some constraints on it, rather than just saying, oh, it's 20, here's all the information about 20, now what if it were some other number? Okay? So we're going to keep red dot there, and we go and we find our x1. Okay. Now, if red dot were 60, we'd bounce right back and we'd be almost at the end. But let's assume it's a little more like 20 degrees, and so our x2 is a little further up here. So these are the same length, and that makes x1, x2 isosceles, and angles opposite the common or duplicated side length are equal. So this angle up here has got to be red dot as well. Okay. Now x3, that's odd, so it's going to have to be somewhere down here. But x2, x3 is also the same length, this common length that I don't think has anything to do with the actual angle, because I think you can sort of scale it. But we have another isosceles triangle. Now I don't know these angles, but we're going to call them green dot. And I can actually relate green dot to red dot. Most of you will have seen this before, but if I just take a triangle and I have, say, dot and check as my angles, not this angle inside, but this angle outside is dot plus check. An exterior angle is the sum of the 2 opposite interior angles. This is an important result to know for triangles. It can make computing angles in questions a lot quicker. So with that in mind, I know that green dot must be red dot plus red dot, or twice red dot. So specifically for our purposes, if red dot is 20, this would be 40. Okay? But I like keeping it as 2 red dot for now. And then I think if we bring one up here, I know it's looking like it's getting longer, but just for our purposes, let's just use our imagination a little bit, it's the same length. So we find our x4 here. We're going to get another isosceles triangle. We're going to get purple dot, let's say, or lavender dot. And then it's going to be the sum of these 2 green dots here. So is it going to be a multiple of 4? We're going to be working with multiples of 8 here. No, actually, what's going to happen is we're going to, I don't know, orange dot up here. So orange dot is 180 degrees minus the other 2 remaining green dots. Okay? But orange dot plus red dot, there's this red dot right here. So plus red dot plus lavender dot is 180 degrees. And when we put those together, work those equations out, we're going to find that twice green dot is actually red dot plus purple dot. Okay? And I know that this is then twice red dot. So that's 4 red dot. And so lavender itself should be 3 red dot. Put those red dots in there. Okay. So we've gone 20, now 40, now 60. I wonder if the next angle we encounter will be 80. So I think x to the 5 is where it started bouncing back. And we're going to have, I don't know, the dark blue dot. We still have an isosceles triangle here. That doesn't change. That's still going around. And now this one, we've got, we can see twice purple dot is the same as green dot. Plus dark blue dot. Okay, and we can put all of these in terms of our starting dot, which is red dot. So purple dot is 3 of those, so we've got 6 purple dot is equal to, or sorry, 6 red dot is equal to, well, the green dots are twice red dot. Plus our dark blue dot. Okay. And then if we rearrange, we have the dark blue dot is 4 red dot. Interesting, interesting, interesting. Okay. And now, if it's 20 degrees, it starts to bounce back. We get sort of this angle right here. And then that becomes x6, and then we have x7, and then we have x8, and then that gets the same line there. So, okay. I think I know what's going on here. I think I got an idea, but we're going to make some observations first. So I think when we bounce back, we get the same path, really. Because what I did is I started here, and then we bounced up, then we bounced down, and then we bounced up, and we hit x5, and then we started bouncing back. Okay? But so that's because I went forward. I went from A to x1. Suppose I went backwards, I would be going along some distance, and I'd get 20 here, and then we'd be going along this distance, and we keep going. But if I had red dot here, this one would have to be red dot, and we'd get green dot, we'd get green dot, and we'd get purple dot, which is 3 red dots, and we would just keep going. This would all work out the same in reverse. But this is x4, this is x5, and we got x4 here. Now what happens is, if we put these together, it's about the angle of A, x4, x5, and A, x5, x4. Those are the angles that I'm really interested in here. Because those are both going to have to be the same. So we do that. I'll put this length here, and so when we combine these two and we ignore all the other lines, we've got A, X4, X5. But each of these, and we've also got the red dot here, but we've got red dot plus the two blue dots has got to be equal to 180 degrees because we've got a triangle here. So we'll just put that in here. But everything here can be expressed in terms of 180 degrees. Each of the dark blue dots was 4 red dots. We've got 8 red dots and a red dot. So we got red dot, and this gives us a total of 9 red dots is equal to 180 degrees, or red dot is equal to 20 degrees. Okay. So now I don't have to analyze reversing the pattern and everything like that. And so what I think happens in general if we have x1, x2, all the way up to x2n, we'll have our A and our B, and we'll start with red dot, and then we'll have xn. We'll just assume it's odd for now. It'll be the reverse picture if it weren't odd. But we sort of have these guys, and then we have, let's use yellow here. We eventually arrive at some angle here. So what are these angles here? So, and these should be integer multiples of red dot, and then we'll get 2 of those plus another red dot, so we'll have some sort of odd number of red dots needs to be equal to 180 degrees. Can I get an expression for these guys here? So when I did x1, it was x2 that got, so the angle at x2 was another red dot. And then the angle at x3, and then x4, and then x5. And x5 was the first one, the first dark blue dot I got. So the angle at x3 was twice. And then the angle at x4 was 3 times. And then the angle at x5 was 4 times. So yellow dot should be n plus 1, or in our original case, 5, x5, minus 1, so that would be just n, times red dot. Okay. I don't think we need to prove it, but just for a moment, let's prove it to ourselves that this pattern works, that we always go up by red dot each time. So suppose I knew I had, k red dot here, and I had k plus 1 red dots here. And I'm worried about this angle right here in my brand new isosceles triangle. Well, we'd have k red dots plus, let's call it x, is going to be the same as 2 k plus 1 red dots. And then if we quickly rearrange, we'll actually see that, yeah, x is going to be k plus 1, or k plus 2 red dots. So the pattern is going to keep working, for those of you who are concerned about that. I know, it's a Cayley competition. We don't need to prove what's going on. We just need to get a sense of the pattern and let it keep going. But if anyone was curious, yeah, we can stop and prove that every time we make a new isosceles triangle, we're going to add another 20 degrees or add another red dot or whatever our starting angle was. Okay? So this pattern does keep going, and that justifies our bigger triangle with the xn and the xn plus 1 and those yellow dots. And each yellow dot is n red dots. Okay? You get the yellow dot at xn plus 1 by just bouncing around the first way, just like we got the first dark blue dot. And then by symmetry, as we noted not a moment ago, we get another one of those angles, but it'll be up at xn at this time. Okay? So that tells me that we start with one red dot, and then we got two of the yellow dots. That's got to be 180 degrees. Well, this is one red dot plus two n red dots, and that's got to be equal to 180 degrees. Or red dot is, or sorry, n plus 2n plus 1 red dots is 180 degrees, or red dot is 180 degrees over 2n plus 1. Okay. So first of all, does that work for our 20 degrees? Okay, if we go back to our original question, with 20 degrees, we bounce around, we go x1, x2, all the way up to 2n here. And that turned out to be 8. So n was 4. And our angle here that we started with, 20 degrees, that's 180 degrees divided by 2 times 4 plus 1, or 9. So yeah, that works. What about, let's compare it to the only other laceable case we know, where we did x1, x2, and then we were back at the start. So n in that case was 1, 2n was 2, 2n plus 1 is 3, 180 degrees divided by 3, that's going to be 60 degrees, and that was the angle we started with the 60 degree case. So it all works out. So now, to make this it's a 2 a little clearer. So to have a red dot which is our starting angle, be acute and an integer. Well, we know if n is 1, we automatically are 60 degrees. And if n were 0, maybe, we'd get 180 degrees. So if we want it to be acute, we need n to be bigger than or equal to 1. That's not that hard. And we need 2n plus 1 to be a factor of 180 degrees. Because if it's not, we're going to get some weird decimal, and it's not going to be an integer. So now we need to sit down and figure out, okay, how many odd factors, giving us, so this would be 2n plus 1 greater than or equal to 3. How many odd factors greater than or equal to 3 are there for 180 degrees? So we analyze the problem at a geometric level. Now we just need sort of to count. Now 180 degrees, that's got a factor of 2, so that's 2 times 90. So it's 2 squared times 45. 45 is 9 times 5, so that's 3 squared times 5. So the 1. So I've written it as it's in its prime factorization, prime decomposition. If I'm ever going to get an odd number, because 2n plus 1 is an odd number, if I'm going to get an odd number as a factor, I need to be looking at... I can't ever use a factor of 2 here. I can't, because as soon as I have a multiple of 2, it's even, not odd, no matter how many other 3s or 5s we add in. So can't use factors of 2 to get odd numbers. That just doesn't work. So really what we're looking for is factors of 3 squared times 5 to the 1, or 45, which aren't the number 1. Number 1 won't work. We'll have to at least have 3. And you could list them out if you want to. So 3, 5, 9, 45 would do just fine. 15, I missed that one. 1 is a factor. We're not going to look at that one, but that is a factor. So the easiest thing to do is just sort of list out the factors. If you have it written like this, you take the 2, you add 1. You take the 1, you add 1. If there were other exponents, you add 1 to each of them and multiply them together. That's 3 times 2. So we get 6 factors of 45. All of them are odd. 3, 5, 9, 45, 15, and 1. These are all of them. We just don't count 1. So we should be looking at 5 factors. And that gives us an answer of C, 5. So that should be our answer. That was an interesting little question. I liked that it blended geometric considerations, and then at the end it became a factoring question. I liked that. I thought that was pretty good, and overall a very nice paper. That's the 2003 Cayley there. So you can join me. I'll be going through the Galois, the 2003 Galois next, and if you want a harder multiple choice contest, you can, of course, join me for the 2003 Fermat, which I'll be going through after the Galois at some point. Or you can always just skip ahead, look at the 2004 Cayley if you're really preparing for the Cayleys or anything like that. Okay. But as always, thank you guys for watching. If you feel inclined, by all means, subscribe, just so you are aware when things are posted and whatnot. But either way, thanks for watching, and I'll see you for the next video.